Welcome to the second part. For the 2020 Tokyo Olympics, the Japanese government aimed to demonstrate their commitment to hydrogen as a clean and safe form of energy for the future. Hydrogen would be used to fuel the Olympic torch, fuel transportation between event locations, and provide electricity to the Olympic Village. In Leeds, in the UK, Northern Gas Networks have presented an innovative proposal to transform the existing natural gas network to a 100% hydrogen network to replace all natural gas use in the area with hydrogen. Leeds would be the first large city in the world completely fueled by hydrogen. The aforementioned cases are two key projects among a list of hydrogen initiatives worldwide. In recent years, interest in hydrogen as an energy carrier has surged. Hydrogen enthusiasts have claimed hydrogen to be the silver bullet for the energy transition. The question remains, will hydrogen be able to live up to those expectations? In this video, I will address the different types of hydrogen and hydrogen's potential role within a sustainable and integrated future energy system. Before diving into the more interesting part, it's important to get some definitions straight. Hydrogen is an energy carrier, used to transfer energy from an energy source to energy demand, in gaseous or liquid form. In general, we distinguish three different types of hydrogen: gray, blue, and green hydrogen. Gray hydrogen is produced by a technique referred to as steam methane reforming, which implies the extraction of hydrogen molecules from a methane product such as natural gas. CO2 is a waste product of this process and is simply released into the atmosphere, contributing to CO2 emissions. Blue hydrogen is produced through the same production process as gray hydrogen, except this process is considered carbon neutral due to the addition of carbon capture and storage, or CCS. CCS is a technique which involves the capture and storage of CO2 emissions following from industrial processes. Empty gas fields in the North Sea could, for example, be reused as such carbon storage facilities. Green hydrogen is produced through a process called electrolysis, which uses renewable electricity to split water molecules into oxygen and hydrogen. Whenever people talk about hydrogen as a sustainable energy technology, it is therefore very important to understand which type of hydrogen they are referring to. Green hydrogen is considered the most sustainable form of hydrogen. However, blue hydrogen may play a crucial role in the transition to a hydrogen-based system. In the next video, I will address the role blue hydrogen might play in the hydrogen economy. But for now, let's take a deeper look into the key drivers behind today's hydrogen ambitions. Although the hype around hydrogen might suggest otherwise, hydrogen is already used extensively around the globe. Present day, hydrogen is mostly used as a feedstock, for example in chemical production processes and steel manufacturing. Therefore, the question arises, what is the future potential of the world's most abundant molecule that has caused its recent hype? In general, there are two main applications for hydrogen which drive the energy industry's interest in hydrogen. First, decarbonization of energy end use, which is difficult or costly to electrify. And second, energy system integration to provide flexibility and reduce system cost. Discussing the first application, renewable electricity generation in the form of wind turbines, solar panels, and hydropower has resulted in electrification of the world's energy supply. However, electrification of certain types of energy demand poses a number of economic and technical challenges. In industry, most manufacturing processes require high-temperature heat. High-temperature heat is technically difficult to electrify. In buildings, electrification of heat demand requires these buildings to be retrofitted to comply with high isolation standards. Newly constructed buildings are already being built with these isolation standards in mind, but existing building stock could cost between 10,000 to 50,000 euros per household to isolate accordingly. In mobility, heavy and/or high-range electric vehicles such as trucks, airplanes, boats are difficult to electrify due to the battery capacity required. As to decarbonize all energy end use, even those that are difficult to electrify, interest in renewable gaseous energy carriers is growing. Presently, there are two main options: hydrogen and biogas. Biogas, like natural gas, is a methane-based gas mostly produced from the breakdown of organic material. For example, biogas can be made from biomass such as food waste or manure. Biogas is considered carbon neutral. Although burning biogas results in CO2 emissions, These emissions are captured in the biomass that's being burned, closing the carbon cycle. Public perception of biogas and the limited supply options have made hydrogen the favorable option over biogas. Not only hydrogen's technically unlimited supply possibilities and zero emissions potential have spurred interest, but also its ability to interconnect electricity and gas sectors. This brings me to the second driver behind the renewed interest in hydrogen: the growing need for energy system flexibility and system integration. In the previous video, I mentioned some use cases of hydrogen in energy system integration. The reason hydrogen is such an interesting energy carrier with respect to system integration is mainly due to three applications. First, hydrogen's ability to be converted from electricity to hydrogen and back again, as in our solar field use case in the previous video, can help relieve the electricity grid by making use of excess capacity in the gas grid to transport energy. Second, hydrogen's gaseous state makes this energy carrier especially interesting for seasonal storage, since gases are cheaper to store than electricity. Seasonal storage of solar production in the form of hydrogen could be converted back to electricity to be used during winter time. Lastly, hydrogen provides potential to reuse existing gas infrastructure. Grid operators worldwide have invested heavily in natural gas infrastructure. With the decreasing use of natural gas to reduce carbon emissions, this infrastructure would become obsolete. However, use of hydrogen could provide a so-called second life for these assets, reducing investment costs in new infrastructure and keeping system costs low. As a result, hydrogen contributes to the objectives of energy system integration: sustainability, system resilience, and affordability. In this video, we have discussed the renewed interest in hydrogen as an energy carrier, spurred by carbon emission reduction targets worldwide. We talked about the different types of hydrogen presently discussed within the sector, which differ in terms of production processes and sustainability. Hydrogen's future potential in the energy system is promising now that natural gas is being phased out. As not all energy end use can be electrified, there's demand for a renewable gaseous energy carrier, such as hydrogen. Lastly, hydrogen can play a crucial role in a renewable integrated energy system. It could help relieve in electricity grid capacity problems, provide seasonal storage, and reuse existing gas infrastructure. In the next video, we will discuss the challenges the future renewable and integrated energy system is yet to overcome. Also, we will conclude this series of 3 videos with a market outlook for possible energy system integration business models and hydrogen.